Now let us consider the third case. See, when boiling point at higher altitudes is considered, at higher altitudes, I mean, as we go to upper atmosphere, pressure goes on decreasing, right? I mean, the atmospheric pressure goes on decreasing. As the pressure goes on decreasing, even the boiling point also goes on decreasing. Based on the same explanation, we can say that the boiling point of water will be less than 100 degrees centigrade at higher altitudes. Just like in pressure cooker case, when the pressure inside the cooker increases, the boiling point is elevated. Here, as we go to higher altitudes, the pressure goes on decreasing. I mean, the atmospheric pressure goes on decreasing. Therefore, the boiling point of water also goes on decreasing. So, it will be less than 100 degrees centigrade. Now, let me give you another interesting point. That is, evaporation reduces the temperature of liquid. See, for this, would actually like to take an example. Example is, hand feels cold when ether is put on it. We know that ether, of course, is more volatile, right? Let us see what happens. Now, when ether is put on hands, immediately the evaporation starts, and within no time it gets evaporated. And we know that during evaporation, molecules having high kinetic energy escape into space above the liquid, right? Now, when molecules having high kinetic energy escape, the remaining molecules, the molecules that are left out on hand, possess lesser kinetic energy, right? Because anyway, the molecules having high kinetic energy have escaped out. Now the molecules having lesser kinetic energy are left out on hand. We know that the average kinetic energy is directly proportional to temperature. Okay. When molecules having lesser kinetic energy are left out, the overall average kinetic energy of the molecules decreases. And we also know that the average kinetic energy is directly proportional to temperature. So therefore, temperature also decreases. That is the reason why hand feels cold when ether is put on it. Molecules having high kinetic energy just go off, leaving behind the molecules having lesser kinetic energy. As a result, average kinetic energy decreases of the overall molecules. And according to kinetic molecular theory of gases, average kinetic energy is directly proportional to temperature. Now, because average kinetic energy is decreased, even the temperature decreases. That is the reason why hand feels cold. Okay. Next. Let us now go for Raoult's law. See, I got two different Raoult's laws. Let me go for the first one. This is for a solution containing a non-volatile solid solute and a volatile liquid solvent. Okay. Solute is non-volatile. Solvent is volatile. Okay. Now let me explain this. Consider a volatile liquid solvent in a closed vessel at a particular temperature. Observe the vapor pressure and record the vapor pressure of pure solvent as P naught. Naught refers to solvent. P naught. Okay. Then now let us add a non-volatile solute to it, to this liquid solvent which is volatile. Let us now add a non-volatile solute. Now see, when the non-volatile solute is added to this solvent which is volatile, what happens? See, when the volatile liquid solvent is taken alone, the surface is occupied only the molecules of the solvent which are volatile, right? Solvent was occupied only by, the surface is occupied only by the volatile solvent molecules. But now when the non-volatile solute is added to it, now these are non-volatile solvent molecules, of course, they mix up thoroughly they mix up thoroughly in the liquid solvent which is volatile. While doing so, they replace some of the solvent molecules on the surface. Right? Now, because some of the solvent molecules on the surface got replaced by the non-volatile solute, what happens? Of course, vapor pressure decreases because now the surface is occupied by both the volatile solvent and the non-volatile solute, right? I mean, the number of solvent molecules which are volatile per unit area will now be less than what it was earlier. Now, when the number of solvent molecules on the surface per unit area is less, obviously the vapor pressure will also be less. Now, let this be the vapor pressure of solution. Now, it is no longer a solvent, a pure solvent. It has now become a solution. We can actually use P or even PS. Let me go with P. Right. Now, as we go on adding the non-volatile solute, what happens? As the non-volatile solute is added, vapor pressure of a solution goes on decreasing, right? So therefore, we can simply give it as vapor pressure of the solution is inversely proportional to the concentration of solute particles. As we go on increasing the non-volatile solute, vapor pressure goes on decreasing because the solute is non-volatile. Vapor pressure goes on decreasing. Now, let me explain it in detail. Let us suppose 100 mm pressure at the beginning to be the vapor pressure of the pure solvent. Just an imaginary value. Now, as we go on adding a non-volatile solute to it, say when some amount of the non-volatile solute is added, the vapor pressure of solution is decreased to 90 mm. And what is the decrease in the vapor pressure of the pure solvent because of the addition of this non-volatile solute? It is 10 mm. Go on adding some more solute. Say the vapor pressure of the solution has now become 80. Now, what is the decrease in the vapor pressure of the pure solvent? It has decreased by 20 mm. Add some more solute. Vapor pressure of the solution, let us say, decreases to 70. Now the decrease in the vapor pressure of pure solvent because of the addition of this amount of The non-volatile solute is 30 mm. Go on adding the non-volatile solute. Say the vapor pressure of the solution becomes 60 mm, decreases to 60 mm. Now what is the decrease in the vapor pressure of the pure solvent? It's 40 mm. Now let me tell you that this is the decrease in vapor pressure of the pure solvent upon addition of non-volatile solute, right? Decrease in the vapor pressure. Technically, we call this lowering of vapor pressure. Lowering of vapor pressure. I mean decrease in the vapor pressure of the pure solvent upon adding the non-volatile solute. Okay, let me now give you some more mathematical expressions. Now, anyway, vapor pressure of the solution is inversely proportional to concentration of solute particles. As the non-volatile solute is added, I mean, as the concentration of the solute is increased, look at this. The vapor pressure of the solution went on decreasing. So these two are inversely related. But at the same time, if you observe the lowering of vapor pressure, see it went on increasing. So we can say that LVP is directly proportional to concentration of the solute particles. Okay, now this is very important. I have one more point to discuss. That is, you know the ratio of this lowering of vapor pressure to the vapor pressure of pure solvent is known as relative lowering of vapor pressure. Nothing but the lowering of vapor pressure, I mean P naught minus P, relative to that of the pure solvent, RLVP. Okay. It's a ratio, of course. Now, let me give you one more point. See, P naught, P naught minus P. All three increase with increase in temperature. As I said, of course, not linear, but exponential overall. The vapor pressure increases. Vapor pressure of the pure solvent, that of solution, even LVP also are dependent on temperature. But this relative lowering of vapor pressure is independent of temperature. This is very important. Okay. Now this is actually called Babos law, because it was experimentally proved by von Babot. Okay. Yes. Now let us see the derivation of Raoult's law. Let me again take the same old thing. So this is a vapor, I mean, this is the volatile liquid solvent whose vapor pressure, of course, is P naught. To this, a non-volatile solute is added. Okay. Now, see the vapor pressure of this particular solution is only because of the solvent, isn't it? Because the solute is anyway non-volatile, right? See, from this, we can actually go for Raoult's law, and this thing can actually be given in the form of a Raoult's law, that is vapor pressure of solution containing a non-volatile solute and a volatile solvent is directly proportional to the mole fraction of solvent, isn't it? Because the vapor pressure of the solution is in fact due to this solvent only, not due to the solute. So this can be mathematically given as P, nothing but the vapor pressure of the solution, is directly proportional to the mole fraction of solvent. A refers to solvent, B refers to solute. Now, simple. This is the vapor pressure of solution, and this is a mole fraction of solvent. As the mole fraction of the solvent increases, I mean, as the quantity of the solvent increases, vapor pressure increases, right? Now, you need to be very careful. Let us remove this proportionality and write a constant. So this, of course, is a constant. P is equal to K into XA. Okay. Now let us take some modifications of this. See if this XA, I mean the mole fraction of the solvent is 1. We know that in case of a binary solution, sum of the mole fractions of the solute and solvent is equal to 1. Now, when the mole fraction of solvent is 1, that of solute is going to be 0, right? Okay, keep it aside. But see, when the mole fraction of solvent is 1, from this we can write it as P is equal to K, isn't it? Now under the same conditions, if I just go for one more thing, under the same condition, that is when XA is equal to 1 and when there is no solute at all, do we call it a solution? See, because there is no solute at all, we don't actually call it a solution. It is no longer a solution, right? So we can say that P is nothing but P naught, because it's no longer a solution when there is no solute at all. It becomes a pure solvent. Okay, now from these two, we can write it as K is equal to P naught, right? We have considered XA as equal to 1 and we have ended up with this K is equal to P naught. Now let me take this into this. Substituting this in P is equal to KXA, what do we get? Therefore, P can be written as P naught into XA, right? K is equal to P naught. Now, P by P naught is equal to XA, right? One minus P by P naught is equal to 1 minus XA. Subtracting from 1, we get this. Now, P naught minus P by P naught is equal to XB, because XA plus XB is equal to 1. Now, this is the mathematical representation of Raoult's law. Started with one particular form of Raoult's law and ended up with this very important form of Raoult's law. See, it can actually be given as the relative lowering of vapor pressure of, say, a dilute solution. I'll tell you why later, but for now, a dilute solution containing a non-volatile solute and a volatile solvent is equal to the mole fraction of solute. So this is Raoult's law. Let me give you one more expression for the same. XB, nothing but the mole fraction of the solute, can simply be given as small n by small n plus capital N. Number of moles of the solute by the total number of moles of solute and that of the solvent, right? So this is your Raoult's law. Okay. Yeah.